All right, so what did you discover playing with the bulbs and batteries?
It's hard to maneuver a small bulb.
Okay. It's hard to maneuver the small bulb. What?
I don't know how to technically say it. Like basically you have to have the light bulb has to be getting charged maybe from both sides of the battery. It can't just be like one side of the battery and then light it. It has to be from both.
Okay.
Complete.
Good. You have to, and you're showing me with your finger, you have to have a complete circuit, right? You have to have a circle. Because if we want the electricity to flow continually in what we call a current, we have to have a circuit. We have to have a closed loop of conductor. So you, for example, took the battery, and when you did this, what happened? Heat. It heated up. Why? Is electricity flowing? Yes, current's running through. Now, this might be a good time to stop and say why. We call this the positive terminal, we call this the negative terminal. But why does the battery produce current?
All the negatives are trying to get to the positives on the other side.
Okay, good. And why do negatives want to get from the negative terminal to the positive? Why is there this difference of a positive charge here and a negative charge here? Okay, there's acid in it that has two different types of metals. And that causes it to be polarized. Anybody do this as a science fair experiment when you were in like third grade? You take the lemon or the potato, you shove two different metals, might be copper and zinc, for example, and then you connect the two wires and you have a battery. You can actually light a small bulb or an LED just with taking the lemon, because it has the acid, and shoving a copper rod in it along with a zinc rod in it, because those two metals, as we learned last year, have different electronegativities. They want electrons at different rates. If one wants electrons more than the other, then guess what? He's going to grab them. And so that difference is what's going on inside the battery. The acid just allows for the electrons to move freely. And so we have a positive terminal, we have a negative terminal. And so the electrons want to go from the negative to the positive, and that's actually what's physically happening, but we don't talk about it that way. We talk in terms of what we call conventional current. And the reason we even have conventional current is because the brilliant man who pioneered work in this field, Benjamin Franklin, posited that it's the positive charged thingies that are moving around. And so we said, okay, the positive charges are moving from the positive terminal to the negative terminal in the circuit. And that's what we call conventional current. It always goes from positive to negative. Now you say, well, I'm smarter than that. I know that it's really the electrons that are free to move. Oh, good. No, they can't. They don't move inside the battery, or else the battery would just die. Right? Yeah, you can picture it as being like a wall, right? But they're separated. And so, yeah, the only choice is to go outside the battery to get the other side. So what's really happening is electrons are moving from negative to positive, but the holes, remember how we talked about holes? If a negative moves, it leaves behind a lonely proton. And so if I have a negative and a positive here, and a positive there, as the negative moves over to cover up that positive, that's the flow of a negative, then before there was a positive charge over here, now there's a positive charge over there, so it looks like the positive charge moved in the opposite direction. And in a little bit, I'm going to show you a demonstration of that. Okay?
First one is what's actually happening.
Yeah, what's actually happening is the electrons are moving. But we talk in terms of conventional current, the positive going from positive to negative. All right? And incidentally, why didn't we just change everything when we found out that it's really the negative things that are moving? Well, for one thing, it would have meant rewriting a bunch of equations and undoing a bunch of other conventions, which is a pain in the butt. But then also, this whole idea of talking about the holes and how the holes move actually reflects a lot of other developments that we have later, and so it's just as convenient, if not more, to keep it as conventional current, even though it's really not what's physically happening. It's a description of what's actually happening too. So, all right. So, this is what we call a what? A short circuit. The reason it's called a short circuit is because it's an easy path. I have a good conductor and I connect positive and negative. It's a path of very little resistance. And so a lot of current's going to go through there. If I break that, then do I have a circuit? No. Do I have current? No. I don't have a flow of charges if I don't have a path for them to flow. But if then I reinsert a resistor in the form of, in this case, your light bulb, now, is there a path to go from positive to negative? Yes, but you must go through the resistor, in this case, the bulb. And let's zoom in on the bulb for a second, because you discovered that it has two parts, right? If I look inside, I'll notice that there's a weld spot right here where the wire is attached to this outside metal casing that has the threads on it. And then the other end of this tiny wire right here dives and goes in the middle without touching that case down here to the bottom where that tip is. And then you notice this black spot right here? It's an insulator to separate the two. So that current, as it comes in through the tip, runs up here, has to go through this really skinny part, which we call the filament. And then the other end's connected to the threads. So when I connect the threaded part and the bulb, the tip part, I complete the circuit and allow electricity to flow through the bulb. And that's when the bulb lights up. What some of you accidentally did was let the foil from here touch the foil from here, causing a what? A short circuit. And when you have a short circuit, more current's going to flow where there's least resistance than is where there's a lot of resistance. So does any electricity flow through the filament in this case where you short circuit like this? Yes. But very, very small amount, and it's not enough to light it up. All right? Now, did it matter if you took that and, I can't rotate it, can I? Oh well. Did it matter if you switched where these two wires connected? No, because this incandescent bulb, right, we call it incandescent because it heats up by the warming of a filament, doesn't matter which direction the electricity is going. It can go this way or it can go that way. Same. incandescent. Let me spell it for you. Incandescent. Did I spell that right? Hopefully I spelled it right. Maybe right. Incandescent bulbs have filaments that heat up when electricity flows through them. Now, what do you notice about the direction of the current in this bulb? Does it always go the same way, or in other words, what happens if we take the battery now and spin it around? Yeah, which way will the current go? It'll still go from positive to negative, which in this case is around this way. So for a battery, the current's always going to flow from the positive terminal of the battery to the negative terminal.
So it appears. Not actually what happens.
Well, from now on, I'm going to speak as if conventional current is all that matters, all that exists. So current flows from positive to negative by convention. So when I put the battery around, according to the bulb, it's going a different direction, but according to the battery, it's still from positive to negative. In other words, the current always flows in the same direction for a battery. And we call that direct current, or DC for short.
Is that why the battery's open?
Mm-hmm. Yes.
Oh, it's the other way around. And direct current means it's always from the positive to
It always flows the same direction, which is from the positive terminal to the negative terminal. We're getting there. All right? Now, let's pick up a few ideas that you've already discovered and give some vocabulary to them. If I have this battery connected to this bulb, if I break apart the circuit right here and zoom in right here on this part of the wire, are there any charges there?
Yes.
Yes?
Wait, the signal was doing
Is it the voice trick or is it the voice trick? Which is it? What would it have to have charges? Protons and electrons. Does this section of wire have protons and electrons? Yes. So it has charges. But what are the charges not doing right now? They're not moving. So the difference between this and this is not the fact that there are charges. There's always charges, but it's the fact that the charges are moving. And what's the symbol for charge? Q. So, come on. You're killing me, Smalls. Don't do this to me. Changing in charge over time, which means what? What's divided by time? means it's a rate. Yeah, it's a derivative with respect to time, which is a rate. So what do we call this change in charge with respect to time? We just described it. If we're, current. And the symbol for current is big I. And it's measured in the unit amps, which, amps, A-M-P. A-M-P, right, amps, which is short for amperes, amps for short, symbol, capital A. So that's the unit. Now, is an amp, an ampere, a base unit or a derived unit? Is it fundamental or is it derived from other?
Derived.
It's derived. So what is an amp? It is equal to Coulomb per second. So an amp is a Coulomb per second. It's the measure of how fast the charges are changing, or in this case, moving. Now, did the charges want to move?
Yes.
Charges just get up one day and say, gosh, I'd like to go over there.
They're attracted.
All right? What do you mean they're attracted?
Because they're negative or positive or whatever. And that's when they want to get to the other side.
Why? Why do they want to get from one point to another depending on what charge they are and what charge is there?
The law of Coulomb's law.
Coulomb's law, which says that there will be a force, an electric force
Because one
between
positive
two charges.
negative makes you go use a negative.
Yes. Or in the case of if it's a positive charge and a positive charge, does it still get forced?
No.
Yes.
Or
It's just
direction.
a repulsive force, right? So, yes, by Coulomb's law, it takes electric forces to move charges. Because charges, like anything, resist changes in their state of being, right? If they're sitting there, they want to keep sitting there. They're moving, they want to keep moving, just like you learned from Newton's first law. So, what does it require then to get those charges to move? A force. And in electricity, we call that force, and actually it's not really a force, but it acts like a force, and you'll talk about where we get it. Next year we'll go in great detail as to where we derive this thing. But we call it voltage. Right? In other words, the battery has a voltage because it's like a little guy in there pushing the charges. Yes, it's the bunny. The bunny pushes the charges. He never gets tired. So, we have voltage. Incidentally, voltage is the push. It's also known as electric potential. And I will expect you to know all three of these terms. Or potential difference. Yes, that's what pushes the charge. Now, what we've been talking about how this movement of charge is analogous to the mechanics you learned first semester, right? That Newton's first law says that things want to keep doing what they're doing, and so if we're going to change that motion, we need an unbalanced force. What does the second law say?
Force equals mass times acceleration.
Good. Net force equals mass times acceleration. In other words, if you have an unbalanced push on something, even that something that resists being pushed will result in a change in its motion. In the world of electricity, who's causing the push? The voltage. In this case, the battery, yes. And what's the resulting change in motion? Yeah, current. And then what's resisting that change or that movement? Resistance. Resistance, then, is measured in ohms, O-H-M-S. The symbol is the capital Greek omega, and that looks like combs. I'm going to clean that up. That's open parentheses. Incidentally, what are the units for voltage?
V.
Yeah, volts. That's a tough one, right? Symbol big V. Okay? So this right here, if this was what? What was this equation? Yeah, Newton's second law of motion. It was one of the, if not the most important equation you learned last semester. If that is true, this is the most important equation you learn this semester. And it is called Ohm's law. It's analogous to the second law in that we have something resisting a change in motion. We have something pushing that thing to then result in a change in motion. Now, I need to camp out on resistance for just a minute, and then we'll do my little demo thing. What affects how much resistance a material or an object has? It's similar to friction, right? It's analogous to friction, and so some of the same factors are going to play in. Just, yeah, in terms of, here's a wire, right? Does this wire have any resistance to the movement of electrical charge? Yes. What types of factors affect how much resistance it has? Okay, the material it's made of, right? If it's made up of a conductor, then the resistance is much lower than if it's an insulator, right? So the material. And all materials have a constant that we call their resistivity. And remember him? Who's this? It's the symbol for density, right? Which is rho. It's the Greek lowercase rho. Same symbol. In this case, it's resistivity. And it's direct. So the higher the resistivity, the higher the resistance. So conductors have a very low resistivity. Insulators have a high resistivity. Right? What else might it depend on?
The length of wire it has to go.
The length of wire it has to go through. Which has more resistance? This much wire or that much wire? That much wire, right? Longer wire means longer resistance. So is that direct or inverse? It's direct. So the length of the wire is directly proportional or directly related to the resistance.
The thickness of the wire.
Yeah, what about the thickness of the wire? If I have a really thin wire as opposed to a really thick wire, which has more resistance? The thin wire. And you can think of it as like water through pipes or straw, right? The smaller, the more contact you have with the edges and what. Right. And so that's going to be what kind of relationship? Inverse. And that's the cross-sectional area. So this little side equation here is going to be important to us. We won't do calculations with it, but I want you to know it qualitatively. It's similar.
You never picked up my quiz. I never picked up your quiz, huh? Well, I'll let you know this.
All right, yes?
So the longer wire
Yes?
was more resistant.
Yes. Now, why does this matter right here? Somebody tell me what I just said, how it relates to that.
Because the resistance of the filament is much higher than of the rest of the wires. It has to slow down the
Good. The filament is very thin, right? It's a very tiny, thin piece of wire. Why? So that the resistance shoots way up, and so that causes it to heat up, and that's what gives off the light and heat energy as it flows through the filament. Right, and we're going to come back to that next time. But yes. Now, what else is important about this little equation? Well, if you ever read the warning signs on an extension cord, what's one of the things it tells you not to do? Don't connect them to each other. You don't take a 100-foot extension cord and connect it to another 100-foot extension cord. Why? If you double the length, what do you do into the resistance? Doubling it, right? If I double the resistance and don't change the thickness, right? I've got double the resistance. That means I have a fire hazard. Instead of putting two 100, it is a fire risk depending on the current flow through it. Yes. I mean, it depends. It's possible. I mean, it depends on a lot of other things too, but there is a risk. Now, instead of putting two 100-foot cables together end to end, you should get a 200-foot cable. Why? What's the 200-foot cord going to be? Thicker. Because if we double the length and double the cross-sectional area, then we can have the same resistance. All right? Okay, we're going to pick up